So this video is going to go through an example problem that corresponds to topic 1.2. I apologize a little bit for the glare, working on getting curtains put up, just haven't quite gotten it there yet. So I hope you can see everything well on the board. What we're going to talk about in this video is interpreting a mass spec or mass spectrum, and then how we can use those numbers to do a couple of different things. So here I have a mass spectrum sketched up on my board. So as a reminder, on your y-axis, it's relative abundance. On your x-axis, it tells you the mass of each isotope. And then the height of the peak or the height of the line indicates how many or the abundance of that particular isotope. So if we look at this one, so this sample has 3 isotopes, one with a mass of 20, one with a mass of 21, one with a mass of 22. Most of them have a mass of 20, so our peak is at 90.48%. A very tiny amount has a mass of 0.27%, or 0.27% has a mass of 21. There we go, that's better. And then a little bit more, just over 9%, has a mass of 22. So just from this, without doing any calculations, we can look at this and go, well, most of my mass is 20. Most of my particles have a mass of 20. The other options are a little bit higher, which means my average mass, my weighted average, is going to be just a little bit higher than 20. So without doing any calculations, I can do that, and then I can go and I can look at my periodic table, and I can look at the average atomic masses that would match this. So we're looking at something that's just a little bit more than 20, definitely not 21 or 22. And it's not going to be lower than 20 either. So fluorine has a average mass of 19, neon is 20.18, sodium is 22.99. That means neon is most likely my source of this spectrum. And I can do that without doing any sort of calculations. I'm just looking at my abundance here. I'm saying most of it has a mass of 20, therefore my average is going to be close to 20. So from this, I can say that this is most likely a sample of neon. Now, if I wanted to actually calculate this, I can use these numbers to come up with the actual average atomic mass based on this sample. So let's walk through that. We're going to use the same example just because it's already up here. Okay, when we do this, we are going to take the mass of the isotope and multiply it by the percent. Now, you have to first convert the percent into a decimal. So 90.48 is 0.9048. 0.27% is 0.0027. 9.25% is 0.0925. So we're dividing each of these by 100 or moving the decimal place 2 places to the left. Now, if you don't have the actual mass of the isotope, because there are actual masses. So for neon isotope, what we say is 20, neon 20, really has a mass of, I think it's like 19.9999 or something like that. If you have the actual masses of the isotopes, you're going to use the actual masses. If you don't, you're just going to use these masses, this ratio of mass to charge, okay? Just depends on what data you're given. And we're going to take each of those masses, multiply it by our percent that's already been divided by 100. So I'm going to take my mass of 20, multiply it by 0.9048, and then I'm going to add to that my mass of 21 multiplied by my 0.0027, and then I'm going to add to that my mass of 22 multiplied by 0.0925. Okay, grab my calculator. And then at this point, we're just plugging it all in. And we get an average of 20.1877. And if we wanted to go and check that number, because that's the convenient thing about calculating average atomic mass, is you always have a periodic table. Your periodic table will tell you what the average atomic mass is, which means your calculated number should be pretty darn close, if not exactly what's given to you on the periodic table. So we get 20.1877. My periodic table tells me 20.18. That's awfully darn close, and I have done this calculation correctly. So you could put these units as AMUs, if you're talking about it in terms of molar mass, you could do grams per mole. So that's how we can use the mass spectrum to just estimate what the average would be and use that to identify. We can also use it to actually calculate what the average would be. You could also fill in some of these blanks. You can treat this like any algebraic equation. If you know what the average is supposed to be, and you know 2 of your percents, well, that's easy. You can figure out you're missing one just by adding these up and subtracting from 100. But you can use these to kind of estimate. If you know that this is your average, you know that you are going to have mostly isotope 20, because that's how you're going to get that close to 20. So we can use these numbers in this logic to kind of go back and forth between our graph and our calculations. This video is going to go through an example for topic 1.3. So this is where we're looking at the elemental composition of pure substances. So we're finding empirical and molecular formulas. So the question here, I'm going to go ahead and read it in case you can't see it because of the glare on my wall. Determine the empirical and molecular formulas for a compound that gives the following percentages on analysis. So whatever the compound is, it's been analyzed and it's been found to have 71.65% chlorine, 24.27% carbon, 4.07% hydrogen by mass. And then we know that the molar mass of the actual compound is 98.96 grams per mole. Now we need to figure out the empirical and the molecular formulas. We're going to start with the empirical formulas. So the first thing you're going to do if you're given percentages is you are going to, the easiest thing is to assume you have 100 grams of the sample. If you have 100 grams of the sample, then your percentages are the same thing as your mass, because 71.65% of 100 is 71.65. So I always like to make that assumption. So we are going to assume 100 gram sample. You don't necessarily have to specify that. I am here just so that if you're following along, you can make that connection between how I'm going to go to the next step. So I can then, if I'm assuming 100 gram sample, say 71.65% chlorine is 71.65 grams of chlorine. Now, remember for our formulas, they are the mole ratios between the elements in a compound. So in order to get to that, we need to convert to moles. So we're going to take each of our percents, turn them into grams by assuming 100 gram sample, and then we're going to convert each of these into moles. So we are going to take, I like to do all of this at once. That's my personal strategy. You could do each of these separately if you like. It's entirely up to you. So we're converting grams into moles, which means we are going to multiply by the reciprocal of the molar mass, or in other words, divide by the molar mass. So I'm going to grab my periodic table. I'm going to look each of these up. Chlorine is 35.45 grams per mole. Carbon is 12.01 grams per mole. Hydrogen is 1.008 grams per mole. Okay, I cannot do that math in my head. So 71.65 divided by 35.45 gives me 2. I'm going to keep this one, I'm going to keep 4 significant figures. So 1, 2, 3, 2.021 moles of chlorine. I'm going to do carbon, which gets me 2.021 moles of carbon as well. And then hydrogen, I get 4.04. I'm only going to keep 3 significant figures because I've only got 3 here. Moles of hydrogen. Now, we need to find the molar ratio of all of these. So what you're going to do is you're going to look at your moles. You're going to pick the smallest one. You're going to divide all of the numbers by that smallest number. Now, we have 2 that are the same, so that makes that easy. So 2.021 is my smallest number. So I'm going to divide everything by 2.021. that means this obviously comes out to 1 chlorine, this one comes out to 1 carbon, and this comes out to 2 hydrogens. Okay, lowest whole number ratios. So I know that I have a formula of CH2Cl is my empirical formula. So that's the first part of the question. Now, just for space, I'm going to do some erasing. So I'm going to write my empirical formula up here so that I don't forget it. Oops. There we go. Empirical formula CH2Cl. Okay. Let's erase the bottom part of my board. Okay, now to get from empirical formula to molecular formula, we're going to use the one piece of information we haven't used yet, which is our molar mass. So this is the mass of the actual compound. So what I'm going to do is I'm going to compare the mass of my empirical formula to my known molar mass. So I'm going to find my empirical formula mass, which is really just the molar mass based off of the empirical formula. Okay, so I've got a carbon, which is 12.01, plus 2 hydrogens, plus a chlorine, which gets me a mass of 49.476. Now, I'm going to compare my empirical formula mass to my molar mass. So my molar mass is 98.96. My empirical formula mass is 49.476. When I divide that, I'm 99% sure it's going to come out to 2. Pretty darn close. Okay, so it comes out to 2.00016. So if I take my smallest number of significant figures, I get 4, which still leaves me with 2.0000, which means that my actual compound is twice as massive as my empirical formula. So I can multiply all of my empirical formula amount by 2. So if I do 2 times CH2Cl, I get C2H4Cl2 as my molecular formula. So my empirical formula is CH2Cl. My molecular formula is C2H4Cl2. And there we have it. We've used our mass percent data and our molar mass to figure out our empirical and our molecular formulas. So now we're going to look at an example for topic 1.4, which is the composition of mixtures. So this particular example has 2 parts. So we're going to do part A first, and then I'm going to erase everything, and then we're going to do part B. So part A says to calculate the mass percent of each element in carbone, which has the formula C10H14O. So this is a pure substance here, okay? So we're going to get to the mixture part here in part B, but right now we're just looking at the pure substance. So pure carbone, we want to know what percent is carbon, what percent is hydrogen, what percent is oxygen. So the first thing you want to do is you want to calculate your molar mass, because what we're going to look at is how much of the total mass is due to carbon, how much is due to hydrogen, how much is due to oxygen. So to do that, we first need to know what our total mass is. So if we add up 10 carbon, 14 hydrogen, and 1 oxygen, we get a molar mass of 150.212 grams per mole. Okay, so now that we know our total, so it's just a percent, so part over the whole. So we know the whole is 150.212. The first part is carbon. So 10 carbons at a mass of 12.01 each divided by 150.212 gets me, I don't know off the top of my head. That gets me 0.7, I'm going to keep 4 significant figures, 0.7995, we want it in a percent, so we're going to multiply by 100. So 79.95% carbon. Going to do the same thing for hydrogen. So 14 hydrogens, each at a mass of 1.008, divided by our total. Gets me, I'm going to keep 4 significant figures again, so 0.09395 times 100 gets me 9.395% hydrogen. And then my last one, oxygen, I only have 1. Molar mass of oxygen is 16. Four significant figures, so 0.1065 times 100 gets me 10.65%. Oops, oxygen. Okay, so pure carbone, I know, has 79.95% carbon, 9.395% hydrogen, and 10.65% oxygen. So now let's look at part B. So in part B of the 1.4 example, it says if a sample of carbone was found to contain 12.03% hydrogen by mass, what can you conclude about the sample? Okay, so our pure sample was only 9.395% hydrogen, which means that our actual sample has more hydrogen in it because it has a greater percent of hydrogen, which means it's getting hydrogen from somewhere else. And since it seems to be unaffected by carbon and oxygen, it must come from something else other than carbon and hydrogen, or carbon and oxygen. So we can conclude that there is another compound in our sample that contains hydrogen that's raising that mass percent. So we can use this information and we can compare the percent of pure with the percent of the impurity to conclude what else is in the sample. In this case, we're not really given any options, so nothing specific, so we just know that the hydrogen has to come from somewhere. If we were given specifics, we could then look at the percent hydrogen in the other compounds to determine what compounds would raise the mass percent of hydrogen compared to lowering the mass percent of hydrogen. So anytime you're asked about an impurity, you're going to be comparing the mass percent of that particular part, whether it's an element or a polyatomic ion or something in a compound. You're going to be comparing the mass percent of pure versus the mass percent in the impure, and that will help you determine what your impurity is or what is contributing to the difference in the mass percent. So now we're going to look at an example for topic 1.5, which is about electron configurations. So we're going to go through 3 examples. We're going to go through a neutral, we're going to go through a positive ion, and we're going to go through a negatively charged ion. So the first one we're going to start with is oxygen. So following the Aufbau principle, we're going to use our periodic table. Oxygen is number 8 on the periodic table, so I know I'm going to start with 1s2, then I'm going to go to 2s2, then I jump across and I go to 2p, and it doesn't quite fill. It's 1, 2, 3, 4. Couple things to note. My energy level is the big number. My block or my orbital is the lowercase letter, and then my superscript tells me the number of electrons that are in that particular spot. There are no commas, there's no significant spaces, they're just written straight across. Okay, so that's oxygen, that's my neutral one. Now we're going to do sodium. When I write electron configurations for ions, I always like to write the neutral first and then modify for the charge. So I like to do this in pencil. In this case, I'm doing it in dry erase marker. Same difference, easy to erase. So sodium is number 11, Aufbau principle starting at the beginning. So we're going to start with 1s2, 2s2, 2p6, 3s1. Okay, now my positive charge here means that I'm going to lose 1 electron. It always comes out of my highest energy level, which in this case I have 3 options. I have 1, I have 2, or I have 3. 3 is my highest. There's only 1 there, so I'm just going to lose that 1 Now, I don't leave it as 3s or 3s0. I just erase the whole thing. So 1s2, 2s2, 2p6 would be the electron configuration for sodium plus 1. Okay, sulfur minus 2, same thing. I'm going to write the neutral and then I'm going to modify for my -2 charge. So following the Aufbau principle, sulfur is number 16. We're going to start at 1, 1s2, 2s2, 2p6, 3s2, 3p4. Now, my -2 charge means that I gain 2 electrons. So just like in sodium, I lost my 1 electron out of my highest energy level, I'm going to gain my 2 electrons in my highest energy level. So I've got 3 options, 1, 2, and 3. 3 is my highest. Now, if I look at these, I have 2 options here. I can either put it in the S or the P. Well, the S is full, the P is not. So I'm going to add my 2 more here. So it had 4. I'm going to add 2 more. So that gets me 6. So 1s2, 2s2, 2p6, 3s2, 3p6. I want to point out, we talked in the general notes about the phrase isoelectronic, so something that has the same electron configuration. Sodium ion, sodium plus 1, is isoelectronic with neon. So if you look at this electron configuration, the neutral element that has this electron configuration is neon. Sulfur minus 2 is isoelectronic with argon. So this electron configuration, while it matches sulfur minus 2, it also matches argon. So we can use the electron configurations to go between, and that's what we mean when we talk about things that are isoelectronic. They have the same electron configuration, but they might have different protons and neutrons, which makes them different elements, but their electrons are the same. Okay, so we're going to look at a couple examples that pertain to topic 1.8. So this is dealing with valence electrons and ionic formulas. So we're going to go through 2 quick examples to remind you of how ionic formulas are written based on their charges. So our first example is sodium oxide. So the first thing you're going to do is you're going to find the charge for each of these ions. So sodium Na, it's in the first column, so it's Na plus 1. Oxide is oxygen, so it's in column 16, yep, right number, which means it has a -2 charge. Now the phrase I like to use is swap and drop. So we're going to swap where they're located, which means I'm going to swap my 2 over to my sodium, my 1 over to my oxygen, and then I'm going to drop them into the subscripts. So my 2 from my oxygen came over to my sodium, dropped into my subscript. My 1 from my sodium went over to my oxygen, dropped into my subscript. And then one last little touch. We don't include 1s in chemical formulas. So the formula for sodium oxide is Na2O. Our next example we're going to look through is another oxide, iron 3 oxide. Notice here this one has a Roman numeral in the middle of the name. That's because iron is a transition metal. So your transition metals are going to have a Roman numeral because that's going to tell you the charge, because you can't get the charge from the periodic table. So my 3 here tells me that my iron has a +3 charge. So the symbol for iron is Fe. So I'm Fe plus 3. Oxide, still oxygen, still a -2. Okay, same process. So I'm going to swap over to the other side, and then I'm going to drop into my subscripts. So that means my 2 from my oxygen swapped over to my iron, dropped into the subscript, so I get Fe2. And then my 3 from my iron swapped over to my oxygen, dropped into the subscript, so I get Fe2O3. So that's what I mean by the phrase swap and drop. So that's how we can go from the names to the formulas for ionic compounds. So the other part to topic 1.8 is knowing that not only do elements have same charges and same numbers of valence electrons based on their column on the periodic table, since those valence electrons are what's doing the reacting, elements in the same column, in the same group, are going to have similar reactive properties. So we can use this to compare the reactiveness between two elements, and we can also do this to compare between two compounds. So you might see a question that says, explain why Cl2, so calcium chloride, is likely to have similar properties to calcium bromide. They both have calcium in them. The difference is the chlorine and the bromine. So that's what we're going to be focusing on, because it doesn't say that they're the same, it says similar. Okay, so if we think about chlorine and bromine and go farther than thinking, if we go to our periodic table, we can see that chlorine and bromine are in the same group, they're in the same column, therefore they're going to have similar reactiveness. Obviously, calcium is going to react like calcium no matter what compound it's in, so that part is going to be the same. It's this part that's different. So when we're looking at why there might be similar properties, we're going to look at what the connection is between these two elements in the compound. These two elements are in the same column, therefore they're going to have similar reactive properties. We could extend this and say, well, chlorine and bromine are in the same column, therefore I can probably say that calcium fluoride and calcium iodide would also have similar reactive properties because those elements are in the same column as well. So you can go both ways. So you can have two compounds and say they're going to have similar properties because they're in the same group. You could also, if this asked which compound might have similar properties to calcium chloride, you'd look for something that's in the same group as one of the elements. So not only do we use the groups on the periodic table to determine formulas based on their valence electrons and therefore charges, but we can also use those valence electrons to talk about their reactive properties based on the fact that they're in the same group. So this is an example for topic 3.2, which is dealing with the photoelectric effect in the electromagnetic spectrum. So we're looking at what happens when light is used to eject photons. So when you get light with a certain wavelength, with a certain amount of energy interacting with a sample, it can eject electrons, and we can measure the speed of those electrons. So in this question, in this example, it says when light hits a metal, electrons are ejected with 3.3 times 10 to the negative 19th joules of energy. What color is the light? So on your periodic table equation sheet, up at the top there is a section with atomic structure, and there's two equations that we're going to use. So we're going to be looking at E equals H nu. Looks like HV, it's H nu. And then we're going to be looking at C equals lambda nu. So lambda is wavelength, and it tells you that on your equation sheet. So it tells you that nu is frequency, E is energy, lambda is wavelength, and C is the speed of light. So your equation sheet tells you what all of those are. You just need to know where to go to look for that information. So in order to determine the color, we need to know the wavelength. So over here I have a table of ranges of wavelengths with their corresponding colors of light. So ultimately I need my number for lambda. So if I'm going to isolate lambda, I'm going to start by dividing each side of this equation by nu. So I get lambda equals C divided by nu. Now C is a constant, speed of light, but I need to figure out what nu is. So that's where this equation comes in. So if I isolate nu, I get nu equals energy divided by H. H is a constant. E is my energy, and I'm given energy in my equation. So I'm going to plug nu in over here, and I get lambda equals C divided by E over H. If I want to simplify that a little bit, that gets me C times H divided by energy. Okay, so C is a constant, H is a constant, E is my energy, which comes from here. So I have all the pieces I need to do to be able to do this calculation. So I'm going to take lambda, and my constant for C is 2.998 times 10 oops, that's what I get for trying to talk and write at the same time, times 10 to the 8th meters per second. And then H is Planck's constant, which is 6.626 times 10 to the negative 34 joules times seconds. And then my E is up here from my question, so 3.3 times 10 to the negative 19th joules. Now, I want to check to make sure that my units cancel. My joules cancel here, my seconds cancel here. It leaves me with meters. We're going to deal with, at the end, meters into nanometers. So at this point, you can, if it's a multiple choice question, you're going to have to do some mental math. So we can round this to about 3. We can do 6.626 is about 6.6, 3.3. So 6.6 divided by 3.3 times 3. So we can do some manipulation there. Since this is not necessarily a multiple choice question, I'm going to go ahead and use my calculator because I don't have it set up as a multiple choice. It might be asked in either way, so you should be comfortable dealing with the numbers in your calculator as well as the numbers as mental math. Oops. And as I say that, I type something in incorrectly. Okay, and I get 6.0. I only get 2 significant figures because I've got 2 here. So 6.0 times 10 to the negative 7th meters. Now I need to get into nanometers, so I'm going to do some quick little dimensional analysis. There are 10 to the 9th nanometers in 1 meter. That is something that's not given to you, so that is a conversion that you should be familiar with. And so then 6 times 10 to the negative 7th times 10 to the 9th gets me 600 nanometers. Now if I go to my table, red is between about 650 and 760, orange is 585 to 647, 600 falls right in the middle of that range. So this light is orange. So all my equations I started with were given to me on my equation sheet, so I don't have to worry about having those memorized. I just need to be familiar with the variables and what they mean, and then how to manipulate the equations to get to one that I can actually use to plug numbers in.